All right, good. So we'll talk briefly about motorized valves. And really, the difference with motorized valves compared to all the other valves we talked about is motorized valves are direct position valves. The motor drives into a position. You're not relying on pressure drop across the valve to modulate them. It's simply a signal, a 420 milliamp signal that drives the valve to a preset position. Where it becomes an advantage, in particular, there's a couple of applications where motorized valves really make a lot of sense. The biggest one I would say though is liquid feed to a vessel, makeup vessel, right? Makeup to another vessel, and the reason for that generally is try not to tell too many stories. The main reason is, so you've got a high pressure liquid to an intermediate vessel, and you might have another intermediate to low, right? And every time you open up a high pressure valve to a lower pressure vessel, what happens?
Increase your pressure.
Yeah, and what happens? You flash, to achieve that lower pressure, you flash off. And so what does that mean to your compressors?
You're working hard.
They work harder. They have to pull down to hold that temperature, right? So what happens is with the solenoid valve, as Phil described earlier, it's an on-off device, right? It's either on or off. Even with a hand expansion valve, the effect is the same. You're metering it, but it's still either on or off. So the compressors don't typically turn on and off on a dime, right? They ramp up, they ramp down. So what happens when unlike the process, if you got a process floor, load drops off. With a liquid makeup valve, it's on or off, and it's in seconds, right? Not over a minute. So you pull the vessel down during that flash gas load that's no longer there. Compressor's geared up for that flash gas load, but you don't have it anymore. So it starts to pull the pressure down in the vessel. When you do that, what happens? Well, the compressors are working harder. If you leave it like that, then what you're doing is you're creating entrained gas in the liquid, and you're pulling that through your pump. So sometimes it'll sound like someone threw a handful of gravel in your pump. That's typically what that is cavitation due to gas entrained liquid. So that's because the compressors are pulling that liquid down, and they're changing the state. So with the motorized valve, what that does is, what that will do, instead of being on and off, a motorized valve will match the liquid makeup requirement. So instead of the flash gas load spiking up and down, with a modulated valve, it might go up, it might go down, but it's going to be consistent and allow your compressors to keep up with that change. So from an energy standpoint, it's been a while since I've looked at it, but it used to be that you guys pay peak rate on your electric or not. Some guys are flat, some guys won't pay peak, right? Peak means, hey, what's the highest point of demand that I need at this facility? That becomes a table that says, oh, okay, you're going to pay for all your electricity, you're going to pay in that peak demand rate. That's in Illinois, I know that's how a lot of them are set up. They pay it on peak, right? Whatever the peak is, that's your average, not your average, but that's what you're paying the rate based on. Because the electric company has to have that amount available to you at all times, not just occasionally. So you pay a higher rate. So what this does is when you have a solenoid valve on and off, you'll see that spike as the compressor pull down, and then it'll drop off as soon as it can. But you're paying on a peak demand. So these valves eliminate the peaks. You'll still have demand, but it won't be peak demand. This video is working good. So one of the challenges, it's an ammonia refrigeration system. There's ice, there's water, there's all sorts of crazy stuff that you run across. So one of the things that we wanted, when we developed this valve, we went through a lot of lab testing, and they'll have environmental testing, which is like IP67, which is like our name of 4, where it's a hose-directed spray. You keep it on the device to ensure that water ingress does not occur. So we passed that. I mean, it was like baby stuff. So we're like, okay, well, what do you have to do, really? There used to be a point where you think about, okay, I have to test to the design point, right? Design point is named for IP67, whatever the case may be. You pass, yes or no? Pass, okay, good. Stop, right? Our philosophy at Hansen is design to failure, right? Design to failure, which means, okay, so we pass IP67, hooray. What do we have to do to get to point of failure. And then when you look at that point of failure, what do you do to eliminate that point of failure beyond the minimum requirements? So really what you saw there was a result of our design to failure that we actually passed in this case. We passed IP67, we said that's not enough, so we submerged the valve in a bucket of water and continued to run the valve underwater. You know, nothing, right? And then someone said, well, that's not real. You know, in a refrigeration system, you're gonna have ice build up, and like, okay, you're right, that's fair. So we end up putting the valve in a block of ice, you know, froze it in the water, and then ran the valve. And that's a prettier picture of it, but that's basically what we did, is we were testing the failure. The only failure we actually had was in our field testing. In our field testing, there was a storm, tropical storm in South Carolina. So we do what we call a 4-point analysis when we do a design. And so, you know, it's easy, kind of the mid-range is there, but what you say is, what are the most extreme applications we can test these valves in? You know, you did the lab testing, okay, everyone feels good about it. You saw some of the results. Now in field applications, what are the extremes, right? What's the lowest temperature? What's the highest temperature? What's the lowest pressure? What's the environmental challenge that we think is the most difficult? What's the cycling application we think? So it's called a 4-corner test. So you set up an experiment, or what we did is our field test was set up around the idea of the 4 corners. Get the extremes, you can hit the extremes, and everything in between you should feel comfortable with. So that's how we approach the design of this valve. And that's why we're so confident in it, is because everything that went into its design. This is Loria, but in our factory, this is an old picture. This is actually off our lab tech. But so every screw, you know, everyone talks about torque. Hey, what's a torque setting, right? So every screw in this assembly cell is counted. Every time it turns, it's counted. And the two things have to match. The number of turns and the torque have to match before it can progress to the next stage. After all that's done, so every screw, every count, every stage is monitored by a computer, and it locks out the fixture. So the worker can't ignore it. The supervisor has to come over and say, no, reject, next valve, please, right? So that's all locked in. And we keep a historical record of every single transaction that we built, every valve that we built. And then the final test, you're going back to the environmental ruggedness piece. That final test is really built around, okay, you did all the things right. Well, what's the final test that's required? So we pull a vacuum on this. So we pull a vacuum on the assembly and measure for any leakage whatsoever, right? And once we pass that test, then the valve's suitable, and the motor and the actuator is suitable for going on one of our valves. I won't kill you with the details here. Lots of pictures and explanations of how it can be used. But this one may be worth looking at a little bit. So unlike the other valves where you have pilot passaging that goes up to a pilot valve and back down, this is directly driven off of the motor. It's a servo motor that directly drives this piston. Inside of here, though, is a hermetic can or containment. So there's an external magnet, and inside of that is a secondary containment. So there's no, like a shutoff valve, you'll have a stem that goes through the pressure containment envelope, the pressure containing envelope. With this, there's no seal to worry about because it's actually magnetically coupled. I guess is a nice way to say it. It's a magnetically coupled driven valve. But because it has a feedback, you know if it's in the right position or not.